Look up at the night sky, and what do you see? Pinpricks of light, distant stars, the occasional streak of a passing satellite. But between those familiar points of light lies something far more mysterious, a vast, invisible ocean of gas, dust, and energy that stretches across the cosmos. This is the interstellar medium, the hidden fabric of space itself, and it's filled with secrets we're only beginning to unravel. Imagine it as a cosmic fog, drifting between the stars, so diffuse you could fly through it for light years and barely notice, yet it holds the building blocks of galaxies, the birthplaces of new stars, and clues to some of the universe's greatest enigmas. What makes this invisible frontier so fascinating? It's where the ordinary rules of physics seem to bend, where temperatures swing from near absolute zero to millions of degrees, and where bizarre particles and magnetic fields dance in ways we still don't fully understand. This isn't just empty space, it's a dynamic, ever-shifting landscape where the universe writes its most puzzling stories. And here's the thing, despite centuries of stargazing and decades of cutting-edge research, the interstellar medium remains one of astronomy's biggest unsolved mysteries. We've sent probes to the edges of the solar system, built telescopes that peer billions of years into the past, and yet this cosmic fog still keeps its deepest secrets locked away. That's exactly why we're diving into the 25 most captivating mysteries of the interstellar medium, questions that challenge our understanding of space itself. Why does it glow in ways that defy explanation? What strange molecules lurk unseen in its depths? How does it shape the birth and death of stars? Each of these puzzles is a piece of a grander cosmic puzzle, and uncovering them could rewrite what we know about the universe. So if you've ever wondered what lies in the shadows between the stars, or why scientists are so obsessed with this invisible frontier, you're about to embark on a journey that will change how you see the night sky forever. The answers, and the even bigger questions they reveal, are waiting. Between the stars, hidden from view, lies a ghostly substance that defies even our most advanced telescopes' vast clouds of dark gas. Picture a thick cosmic fog, so faint it barely whispers its presence, yet stretching across light years of space. These invisible reservoirs hold the raw ingredients for new stars, but they refuse to play by the rules of observation. Unlike the vibrant nebulae that dazzle with color, dark gas operates in what you might call cosmic stealth mode, absorbing light instead of reflecting it, leaving astronomers to piece together its secrets through indirect clues. So what exactly is this mysterious material? Mostly cold hydrogen, the universe's most abundant element, laced with trace molecules like carbon monoxide. But here's the twist. At temperatures just a few degrees above absolute zero, these gas clouds don't emit the energetic light signatures telescopes typically hunt for. Instead, they cloak themselves in darkness, detectable only by the way they blot out the stars behind them like a silhouette against a cosmic backdrop. Why does this matter? Because these shadowy clouds are cosmic cradles, places where gravity slowly pulls matter together until pressure and heat ignite new stars. But how exactly does something so diffuse collapse into something so brilliant? That's the puzzle. Even more baffling is how these clouds maintain their structure despite the chaotic turbulence of space. Magnetic fields might play a role, acting like invisible scaffolding, but the full story remains hazy. Think of it like trying to study a snowstorm by watching the flakes vanish before they hit the ground. Astronomers must rely on radio waves and subtle distortions in starlight to map these hidden realms. Every glimpse reveals new questions. Why do some clouds birth stars while others linger dormant? What triggers their transformation? The answers could rewrite our understanding of how galaxies evolve, one invisible wisp at a time. From the depths of space, an invisible rain constantly pelts our planet, not water, but particles moving at nearly the speed of light. These are cosmic rays, high-energy fragments of atoms hurtling across the galaxy with enough force to punch through solid matter. Discovered over a century ago, they remain one of the interstellar medium's most enduring riddles. Where do these tiny bullets of energy come from, and what cosmic catapult could fling them with such violence? The leading suspects lurk in the aftermath of stellar explosions, supernova. When a massive star dies, the shock waves from its collapse ripple through surrounding gas clouds like tsunamis, potentially accelerating particles to unimaginable speeds. Picture a surfer catching a wave, but instead of ocean water, it's a wall of plasma propelling electrons and atomic nuclei to energies that dwarf anything produced in human-made colliders. Yet supernova might not be the only culprits. Some cosmic rays carry so much energy that even these stellar cataclysms can't fully explain them. Enter black holes, particularly the supermassive ones at galaxy centers, where swirling magnetic fields could act as natural particle accelerators on a gargantuan scale. Here's where the mystery deepens. While we've traced lower energy cosmic rays to our galactic neighborhood, the most energetic ones seem to arrive from voids between galaxies, suggesting even more exotic origins. Some theories point to colliding galaxy clusters or hyperactive quasars, but the truth is, when these particles finally reach Earth, their paths are so scrambled by interstellar magnetic fields that tracing them back is like trying to find the source of a single raindrop in a hurricane. What makes this puzzle so vital? Cosmic rays are more than just space oddities. They shape the chemistry of interstellar gas, influence star formation, and may even play a role in life's origins by triggering chemical reactions in cosmic clouds. Unlocking their secrets would give us a front-row seat to the universe's most extreme physics, from the ruins of dead stars to the engines of active galaxies. Until then, every particle that streaks through our atmosphere carries a coded message we're still learning to read. For over 100 years, astronomers have been staring at rainbows from distant stars and finding dark lines that no one can explain, like hidden messages written in starlight itself. These are the diffuse interstellar bands, ghostly absorption lines etched into the spectrum of starlight as it passes through cosmic clouds. Think of them as chemical fingerprints left by unknown substances drifting between the stars. But here's the catch. After decades of lab experiments, we still can't match these fingerprints to any known molecule on Earth or in space. The mystery starts with the sheer range of these bands. Nearly 600 have been catalogued, each representing a different wavelength where light gets absorbed. Some are narrow and sharp, others broad and fuzzy, suggesting a whole zoo of mysterious compounds floating out there. The most tantalizing clue: these bands appear strongest in regions rich in complex carbon molecules, hinting at organic chemistry on a cosmic scale. Yet every time scientists try to recreate the conditions in a lab, chilling gases to near absolute zero, blasting them with radiation to mimic space, the puzzle only deepens. The signatures never quite match. What could these enigmatic molecules be? Polycyclic aromatic hydrocarbons, long-chain carbon compounds, even exotic forms of hydrogen have all been proposed. Some researchers speculate they could be entirely new classes of compounds, forged in the extreme cold and low density of interstellar space where chemistry behaves strangely. Others wonder if we're seeing the handiwork of nanoscale carbon structures like tiny cosmic graphene flakes. The implications are staggering. If these bands represent unknown forms of matter, they could rewrite our understanding of how complex molecules form in the universe. And then there's the bigger picture. These bands aren't just curiosities, they're tracers, revealing the hidden structure of gas clouds and the chemical pathways that might lead to life's building blocks. The fact that we can't identify them yet is a humbling reminder. For all our advances, the cosmos still holds chemistry textbooks we haven't opened. Every unanswered band is a whisper from the dark, waiting to teach us something new about the universe's hidden ingredients. Imagine counting every grain of sand on a beach, only to discover a third of them have vanished without a trace. That's essentially the dilemma astronomers face with the interstellar medium. where a staggering 30% of the ordinary matter we expect to find has mysteriously disappeared. This isn't dark matter, that other cosmic enigma, but actual atoms of hydrogen and helium that should be floating between stars, yet stubbornly refuse to show up in our observations. Where could they be hiding? One leading theory points to an invisible ocean of million-degree gas, so hot it's practically transparent. Picture steam rising from a boiling kettle. Except this steam is spread across the voids between galaxies, glowing faintly in X-rays but too diffuse for most telescopes to spot. These ultra-hot filaments, part of the so-called cosmic web, might weave through the universe like an invisible scaffold, cradling galaxies while eluding detection. Satellite observations have glimpsed hints of this superheated gas, particularly in galaxy clusters, but the numbers still don't add up. The mystery deepens when you realize this gas should leave distinct wrinkles in the cosmic microwave background, the afterglow of the Big Bang, yet those fingerprints remain frustratingly faint. Then there's the wild card. Could this missing matter be tangled up in something even stranger? Some researchers speculate it's locked away in exotic, diffuse structures, clouds of cold gas so vast and thin they're virtually undetectable, or even bizarre, lightweight dark matter particles interacting with ordinary atoms in ways we don't yet understand. Others wonder if the answer lies in plain sight, with measurement errors or overlooked processes in how galaxies eject material into space. The stakes couldn't be higher. This isn't just about accounting for stray atoms, it's about testing whether we truly understand the universe's inventory of stuff. If the missing matter is hiding in hot gas, it would reveal a hidden backbone of cosmic structure. If it's tied to dark matter, it could rewrite the rules of particle physics. Until we solve this puzzle, every map of the cosmos we draw is fundamentally incomplete, like a jigsaw with critical pieces still lurking in the shadows. Stars live extravagant lives, burning bright and dying spectacularly, but their greatest legacy might be what they leave behind. Across billions of years, they've been quietly reshaping the cosmos by spewing their insides back into the interstellar medium, a process we've come to call galactic recycling. Picture a cosmic loop where stars fuse hydrogen into heavier elements like carbon, oxygen, and iron, then scatter those ingredients into space through violent explosions or gentle stellar winds. These enriched materials become the building blocks for new stars, planets, and even life itself. But here's the catch: our models can't quite explain how this recycling happens so efficiently. Take supernova, the universe's ultimate recyclers. When a massive star explodes, it doesn't just blast debris randomly. It carves out enormous tunnels in the surrounding gas, like cosmic chimneys funneling heavy elements upward into the galaxy's higher altitudes. These structures, sometimes stretching hundreds of light years, allow enriched material to spread far and wide instead of clumping near the explosion site. But simulations show a problem. Without some hidden mechanism helping distribute the material, much of it should fall back into the galaxy's denser regions, pooling rather than dispersing. So what's keeping the cycle moving? Some theories point to magnetic fields acting like cosmic conveyor belts, or even the combined push of countless stellar winds from neighboring stars clearing paths for the flow. And then there are the quieter contributors, stars like our Sun, which shed their outer layers gradually through solar winds and planetary nebulae. These gentler outflows may not make headlines like supernova, but they're just as vital, peppering space with lighter elements like nitrogen and carbon in a slow, steady drizzle. Yet even here, the numbers don't quite add up. Observations show more heavy elements floating between stars than our current recycling models predict, as if the galaxy has hidden factories churning out extra enrichment. The implications are profound. If we can crack how this galactic recycling works so effectively, it could rewrite our understanding of how galaxies evolve and why certain regions of space become fertile grounds for new stars and planets. Every atom in your body was once part of this grand cycle, forged in the heart of a long dead star and scattered across the cosmos. the mystery isn't just about astrophysics, it's about tracing the journey of stardust itself. In the cold, sparse depths of interstellar space, a simple chemical conundrum defies expectations: carbon monohydride, or CH+. This humble molecule, just one carbon and one hydrogen atom linked by an invisible thread, shouldn't exist in the quantities we observe. Here's why: space is too empty, too cold, and too calm for CH+ to form easily. Its creation requires a violent collision of atoms at high speeds, like two needles meeting in a cosmic haystack the size of a continent. Yet somehow, telescopes reveal it surprisingly common, glowing faintly in the infrared like a beacon from the void. The key to this mystery lies in turbulence, the invisible storms raging through interstellar clouds. Picture shockwaves rippling through these gas formations, triggered by supernova explosions or the fierce stellar winds of newborn stars. These chaotic surges act like cosmic mixers, hurling particles together with enough energy to forge CH+ bonds against all odds. It's as if the universe has a hidden forge, one that operates not with fire but with raw, kinetic fury. But there's a twist. CH+ is fragile, easily torn apart by the same harsh radiation that floods space. For it to persist, these molecules must be constantly replenished, suggesting an ongoing cycle of creation and destruction. Some regions show CH+ concentrations 1,000 times higher than standard models predict, pointing to gaps in our understanding of how energy moves through the interstellar medium. Could magnetic fields be funneling energy in ways we can't yet see? Or are there undiscovered processes at work, something beyond mere shockwaves? The implications stretch far beyond one peculiar molecule. CH+ acts as a tracer, revealing the hidden pathways of energy through cosmic clouds. Where it glows brightest, we're essentially mapping the universe's hidden power grid, the conduits that shape star formation and galactic evolution. Cracking this puzzle could rewrite how we model the life cycle of interstellar gas, showing us not just where stars are born, but how the chaos of space fuels their creation. Every flicker of CH+ light is a clue, a whisper from the turbulent heart of the cosmos, and right now we're only beginning to listen. They shouldn't exist, not in these numbers, not in these conditions. Microscopic grains of dust, each no larger than a speck of smoke, drifting through the violent expanse of interstellar space, bombarded by radiation that should rip them apart, frozen in temperatures that ought to turn them brittle, and yet here they are, cosmic survivors defying every expectation. These aren't just any particles, they're the universe's unsung architects, the hidden scaffolding upon which planets are built. And their secrets might rewrite how we understand the birth of solar systems. At first glance, interstellar dust seems straightforward, tiny flecks of silicates, carbon, and ice, forged in the furnaces of dying stars and scattered across galaxies. But look closer and the anomalies pile up. For one, they're absurdly resilient, bathed in ultraviolet radiation from nearby stars, blasted by shockwaves from supernova. These grains should shatter or evaporate in a cosmic blink. Yet somehow they persist, cloaked in bizarre organic mantles that act like radiation armor. Laboratory experiments reveal their trick. Complex carbon molecules coating their surfaces absorb and dissipate energy, turning potential destruction into mere weathering. It's as if these particles have evolved their own sunscreen, tailored for deep space. Then there's their shape, fluffy, porous, and utterly unlike anything we'd expect. Imagine grabbing a handful of snow, but instead of compact ice, the flakes are hollowed-out labyrinths with more empty space than solid material. This structure isn't just odd, it's transformative. When these grains collide in the depths of nebulae, their delicate frameworks tangle like cosmic Velcro, sticking together instead of bouncing apart. Over millennia, this gentle clumping builds the first pebbles of future planets, bypassing the sticky problem of how solid matter consolidates in the vacuum of space. But the real mystery lies in their diversity. Some grains resemble miniature sponges, others tangled chains of beads, and a few even mimic the structure of fractal snowflakes. Where does this variety come from? Observations suggest dust in one nebula might differ radically from dust just a few light-years away, as if each star-forming region has its own unique recipe. Could this explain why some planetary systems form rocky worlds, while others spawn gas giants? The answer might be coded in these microscopic architectures. What's at stake isn't just academic curiosity. These grains are time capsules carrying the elemental blueprints of their parent stars. Locked within their intricate shapes are clues to how carbon, oxygen, and silicon, the raw materials of life, get distributed across galaxies. Every exoplanet we've discovered, every distant moon, even Earth itself began as a swirl of this enigmatic dust. To understand it is to trace our own cosmic ancestry, back to the moment when stardust first dreamed of becoming something more. Deep within the interstellar medium, an unseen force weaves through the cosmic gas and dust magnetic fields so subtle they're more like whispers than shouts, yet powerful enough to sculpt entire galaxies. Imagine trying to map the wind by watching how it bends blades of grass. That's the challenge astronomers face when studying these invisible strands. They leave no direct imprint on light, no shadow or glow, yet their presence is everywhere, twisting nebulae into spirals, guiding the collapse of star-forming clouds, and even channeling the paths of cosmic rays. Without them, the universe as we know it would look radically different. But how do you measure something you can't see? The answer lies in starlight itself. As light travels through space, the electrons in interstellar dust grains align with these hidden magnetic fields like tiny compass needles. When the starlight hits these aligned grains, its polarization shifts ever so slightly, a twist that sensitive telescopes can detect. It's like reading secret messages written in the faintest ink, requiring instruments like the Planck satellite or the Stratospheric Observatory for infrared astronomy to catch these subtle cues. What they've revealed is astonishing. Magnetic fields aren't just passive backdrops but active players, stretching across light years with strengths that vary wildly from one region to another. Some areas show fields neatly combed in parallel lines, while others are chaotic tangles, as if space itself is caught in a cosmic whirlwind. But here's the puzzle. These fields shouldn't be this strong. According to conventional models, the diffuse gas of the interstellar medium is too thin to sustain such powerful magnetism over vast distances. Yet observations suggest otherwise, pointing to undiscovered mechanisms, perhaps turbulent gas motions acting like dynamos, or the cumulative effect of countless stellar explosions pumping energy into the fields over eons. Even stranger, some clouds exhibit magnetic fields that seem to pinch at their edges, as if an invisible hand is squeezing them into shape. Could this explain why certain gas clouds fragment into stars while others remain dormant? The implications go far beyond curiosity. Magnetic fields are the unseen architects of star birth, determining whether a cloud collapses symmetrically into a single massive star or fractures into a stellar nursery. They also regulate the flow of heat and particles through interstellar space, effectively setting the thermostat for chemistry that might lead to life's building blocks. And when dying stars explode, these fields funnel their ejected material into space, seeding future generations of cosmic structures. Yet for all their influence, we've only begun to sketch their true extent. Every new detection peels back another layer of the mystery. Are these fields relics from the early universe, frozen in time, or are they constantly regenerated by the churning of galactic matter? The answers might rewrite not just our understanding of the interstellar medium, but the very forces that shape the cosmos. Until then, we're left listening to the whispers of magnetism, decoding a language written in the fabric of space itself. Scattered like frozen islands in the sea of space, some of the densest pockets of gas in the universe defy the most basic rule of cosmic physics. They refuse to collapse. These are cold molecular clumps, regions so packed with matter that by all rights they should have crumpled under their own gravity long ago, igniting into new stars. Yet there they sit, suspended in a state of near-perpetual stillness, as if time itself has paused. What's holding them up? The answer could rewrite our understanding of how stars are born, or why some cosmic nurseries never wake up. At first glance, the math seems simple. Gravity pulls gas inward until the pressure triggers nuclear fusion, the spark of a new star. But in these mysterious clumps, temperatures hover just 10 degrees above absolute zero, with densities hundreds of times greater than typical interstellar clouds. Under those conditions, collapse should be inevitable, yet something invisible is propping them up like a cosmic counterweight balancing the scales. The prime suspects, magnetic fields threading through the gas like a spider's web, exerting enough outward pressure to stall gravity's pull. Picture a balloon resisting being squeezed, except here, the squeeze comes from an entire cloud's worth of mass, and the pushback is woven from invisible lines of force. But magnetism might not be the only hero. Turbulence, the same chaotic churn that stirs interstellar gas into swirling eddies, could also play a role. Think of it as cosmic whitewater, with waves of energy crashing through these clumps, disrupting any orderly collapse. Simulations show that under the right conditions, this turbulence acts like a perpetual motion machine, recycling energy fast enough to keep gravity at bay. The catch: turbulence usually dissipates quickly in space, leaving scientists puzzled over how these clumps maintain their frenetic inner storms for millions of years. The plot thickens when we examine their chemistry. These clumps are rich in molecules like carbon monoxide and ammonia, which should radiate away their energy and cool even further, hastening collapse. Instead, they seem locked in equilibrium, as if some unseen hand is adjusting the thermostat. One radical theory suggests cosmic rays, those high-energy particles streaking through space, might be injecting just enough heat to offset the cooling, creating a fragile balance between fire and ice. The implications stretch far beyond these frozen anomalies. If magnetic fields or turbulence can stall star formation so effectively, it could explain why some galaxies produce fewer stars than expected. These clumps might be cosmic pause buttons, hiding reservoirs of material that could fuel star birth or remain forever dormant. Every one we study is a test case for the universe's most fundamental forces, a laboratory where gravity, magnetism, and chaos vie for control. Unlocking their secrets wouldn't just solve a puzzle, it would reveal the hidden thresholds that decide whether gas becomes a star or remains a shadow in the dark. Shine a light through the cosmic fog, and something strange happens. Like sunlight filtering through a dense forest, distant quasar beams emerge with eerie stripes of missing color. This phenomenon, called the Lyman Alpha Forest, isn't just an astronomical curiosity, it's a hidden record of the universe's skeleton, etched in the fingerprints of hydrogen gas. Here's how it works. As light from quasars, those brilliant beacons powered by supermassive black holes, travels across space, it passes through clouds of neutral hydrogen. These clouds act like cosmic filters, absorbing specific wavelengths of light and leaving dark lines in the quasar's spectrum. The result, a barcode of shadows stretching across billions of light years, each line a snapshot of the universe's structure at a different point in time. But the real mystery lies in the patterns these lines create. Instead of neat, evenly spaced marks, the Lyman Alpha Forest is tangled and chaotic. Some lines clump together like trees in a thicket, while others stand isolated like solitary oaks. This isn't random. Each clump traces the filaments of the cosmic web, the vast network of gas and dark matter that forms the universe's scaffolding. Yet for all they reveal, these shadows guard their own secrets. Why do some regions of space show dense thickets of absorption lines while others are sparse? And how does this hydrogen fog, which should be nearly invisible, manage to imprint itself so vividly on light that's been traveling since the universe's youth? Part of the answer lies in temperature. Hydrogen gas absorbs light differently depending on whether it's cold and serene or hot and turbulent. The variations in the Lyman alpha forest hint at unseen forces, cosmic winds from galaxies, shockwaves from long-dead stars, even the gravitational pull of dark matter, tugging at these clouds like invisible puppeteers. But there's a catch: the forest is too noisy. Simulations predict smoother, more uniform patterns than what we observe, suggesting gaps in our understanding of how gas moves and clusters across cosmic time. The most tantalizing clues come from the forest's oldest lines, dating back to when the universe was just a few billion years old. These ancient shadows show far more structure than modern ones, implying something fundamental about the interstellar medium has changed. Was the early universe simply richer in hydrogen, or were its physical conditions, its turbulence, its radiation wildly different? Every quasar's spectrum is a time capsule, and buried in its stripes might be the key to how galaxies grew from primordial fog into the glittering cities of stars we see today. Yet for now, the forest keeps its deepest secrets, its shadows whispering of a universe far more intricate than we've begun to map. Among the dark canvases of interstellar space, certain nebulae shimmer with an eerie infrared glow, a signature not of stars or gas but of soot. These ghostly lights come from polycyclic aromatic hydrocarbons, or PAH, complex carbon molecules that look like microscopic honeycombs under a microscope. Imagine flecks of grill scrapings after a barbecue, but instead of clinging to a grate, they're drifting between the stars, some containing dozens of carbon atoms linked in intricate rings. Their discovery rewrote our understanding of cosmic chemistry, proving the interstellar medium isn't just a void. It's a sprawling laboratory cooking up compounds we once thought required planetary conditions. Yet how these molecular soot stains form remains one of the dirtiest mysteries in astrophysics. One school of thought points to dying stars as the primary chefs. When carbon-rich suns exhale their outer layers in their final years, they create a cauldron of conditions perfect for pH formation. Hot enough to break apart molecules, but dense enough for them to reassemble into these resilient carbon lattices. It's like tossing a handful of puzzle pieces into a hurricane and expecting them to land as a completed mosaic. But here's the catch: some nebulae packed with pHs show no traces of recent stellar deaths nearby, leaving astronomers scratching their heads. This gap in the theory opens the door to a wilder possibility: that pHs might assemble spontaneously in the cold, thin depths of interstellar clouds, where chemistry follows rules we're still deciphering. Lab experiments reveal that when simple carbon molecules are zapped with radiation mimicking cosmic rays, they can stitch themselves into pH-like structures without the extreme heat of stars. It's as if the universe has a slow cooker setting where time and patience, not just stellar furnaces, build complexity. The implications spiral outward from there. These molecules are more than cosmic curiosities, they're survivalists. pHs thrive where other compounds would shatter, thanks to their ringed structures that disperse energy like a boxer rolling with punches. That resilience lets them become interstellar taxis, potentially ferrying carbon, the backbone of life, across galaxies. Some scientists even speculate that pHs could have seeded early Earth, delivering raw materials for probiotic chemistry. Yet for all their ubiquity, pHs guard their origins fiercely. Telescopes like the James Webb Space Telescope are now mapping their infrared glow across nebulae, revealing distributions that don't always match stellar activity. Some regions show pHs concentrated in bizarre, spindle-shaped formations, as if sculpted by unseen magnetic fields. Others exhibit molecular varieties so large they blur the line between soot and fledgling carbon crystals, hinting at a continuum between pHs and the seeds of future planets. The deeper we look, the more these sooty molecules defy categorization. Are they the ashes of dead stars or the building blocks of worlds? The answer might be both, a reminder that in the interstellar medium, destruction and creation are often two sides of the same cosmic coin. Every flicker of their infrared light is a clue, waiting to reveal how chaos and order conspire to paint the universe with chemistry's richest palette. Lithium, the third element forged in the fiery dawn of the universe, is playing a cosmic disappearing act. According to Big Bang nucleosynthesis, our gold standard for how light elements formed in the universe's first minutes, there should be 3 times more lithium floating between the stars than what telescopes actually detect. It's as if someone snuck into the cosmos's pantry and pilfered 2 out of every 3 lithium atoms, leaving astronomers scratching their heads. Where did it all go? The prime suspects are stars, those celestial element shredders, but the case isn't nearly that simple. Take stars like our Sun, for instance. Their outer layers churn like boiling water, dragging lithium down to scalding depths where nuclear reactions destroy it. This explains why older stars show lithium depletion. But here's the twist: younger stars, still rich in the gas of their birth clouds, also lack expected lithium levels. That suggests the theft isn't just happening inside stars. It's occurring out in the open interstellar medium where lithium should be safe. Could interstellar chemistry be quietly erasing it? Laboratory experiments reveal one possible culprit: cosmic dust. Lithium atoms might be sticking to these microscopic grains, vanishing from gas phase observations like footprints fading in snow. Others propose even wilder mechanisms, like lithium being shattered by high-energy photons or transformed into heavier elements through rare nuclear reactions in gas clouds. Yet the plot thickens when we peer at different cosmic neighborhoods. Some dense molecular clouds show lithium locked up in molecules like lithium hydride, while diffuse regions seem to have lost it entirely. This patchiness hints that the interstellar medium isn't just a passive backdrop. It's an active participant in the lithium crisis with processes we've barely begun to map. Magnetic fields might play a role, guiding lithium ions into regions where they're more likely to bond or be destroyed. Or perhaps supernovae, those titanic element forges, are belching out products that react with lithium, pulling it out of circulation. The stakes couldn't be higher. Lithium isn't just another element, it's a benchmark, a relic from the universe's first 3 minutes. If our models can't account for its vanishing act, we might be missing something fundamental about how matter behaves across cosmic time. Every undetected lithium atom is a clue, a whisper from an era before stars or galaxies existed. Solving this mystery could force us to rewrite the recipe for the early universe or reveal entirely new chapters in interstellar chemistry. For now, the missing lithium remains a cosmic cold case, its fate scattered somewhere between the stars and the secrets they keep. Drifting through the darkness at the edges of our galaxy, massive clouds of hydrogen gas streak across the sky at speeds that defy gravity's grasp, some racing at hundreds of kilometers per second. These are high-velocity clouds, mysterious celestial nomads that shouldn't exist according to our understanding of galactic mechanics. Imagine a freight train barreling through a quiet neighborhood, except instead of tracks, this train is an invisible river of gas stretching thousands of light years, and no one can agree on where it came from or where it's headed. The enigma begins with their motion. Most interstellar gas moves in predictable orbits around the galaxy, bound by its gravitational pull like leaves caught in a whirlpool. But these clouds zigzag wildly, some hurtling toward us, others fleeing as if launched by some cosmic slingshot. Early astronomers assumed they were mere gusts in the galactic wind, perhaps debris from nearby supernovae. Then came the shocker. Many originate far beyond the Milky Way's disk, in the desolate halo where almost nothing should reside. 2 competing theories vie to explain their origins. The first paints them as intergalactic invaders, ancient relics of the cosmic web, falling into our galaxy from the void. Picture tendrils of primordial gas, untouched by stellar furnaces since the universe's infancy, finally succumbing to the Milky Way's gravity. Their chemical fingerprints support this. Some clouds show barely any heavy elements, as pristine as the hydrogen that filled the cosmos before the first stars ignited. But the second theory turns the narrative inside out. These clouds might not be intruders at all, but fugitives ejected from our own galaxy in a phenomenon called a galactic fountain. When massive stars explode, their shockwaves can fling gas upward like a geyser, sending it arcing hundreds of thousands of light years into the halo before it cools and rains back down. Simulations show these fountains could explain the clouds' trajectories, but there's a hitch. Some clouds move too fast, their velocities exceeding what even the most violent stellar explosions should produce. The plot thickens when you examine their structure. Some clouds, like the famous Smith cloud, streak toward us in eerie filamentary strands as if stretched by unseen forces. Others, like Complex H, loom ominously in the galactic halo, their sheer mass millions of times heavier than the Sun, challenging any ejection scenario. Magnetic fields might play a role, acting as invisible rails guiding their motion, but measurements remain frustratingly elusive. What's at stake isn't just a cosmic whodunit. These clouds could be the Milky Way's lifeline, delivering fresh gas to fuel future star birth, or they might be ticking time bombs, carrying enough mass to warp our galaxy's structure. Every observation peels back another layer, revealing a universe far more dynamic and interconnected than we ever imagined. The answers, much like the clouds themselves, remain just out of reach, drifting in the shadows between galaxies. Around certain stars, space isn't just empty, it's a roiling sea of million-degree plasma, bubbling like water in a cosmic kettle. These aren't your average stellar winds or gentle outflows. These are titanic structures called hot gas bubbles, glowing fiercely in X-rays and stretching light years across the interstellar void. Their very existence is a paradox. At temperatures that should vaporize anything nearby, they stubbornly hold their shape against the frigid backdrop of space, defying the laws of thermodynamics like a flame that refuses to flicker out. So what's keeping these celestial pressure cookers intact? The leading theory points to relentless energy injections from the stars themselves, specifically massive stars and their ferocious stellar winds. Picture a hurricane blowing non-stop for millions of years, but instead of air, it's a supersonic barrage of charged particles. When these winds slam into slower-moving material ejected earlier in the star's life, they create shockwaves that heat the gas to X-ray, emitting extremes. It's like a cosmic traffic pileup where the collisions generate enough heat to power a small galaxy, yet even this explanation falls short. Simulations show the bubbles should cool and dissipate far faster than they do, suggesting an invisible energy source is at work, perhaps turbulent magnetic fields trapping heat like a thermos, or even unseen particle acceleration events within the bubbles themselves. Then there's the puzzle of their longevity. Some bubbles persist long after their parent stars have died, lingering like ghostly echoes in the interstellar medium. The famous Orion Eridanus superbubble, for instance, spans over 1,000 light years and glows with the remnants of ancient stellar fury. But without ongoing energy input, these structures should have collapsed into the surrounding gas eons ago. One radical hypothesis suggests cosmic rays, those high-energy particles zipping through space, might be pumping energy back into the bubbles, effectively recharging them from within. It's a bit like a campfire that keeps burning because someone keeps tossing in dynamite. The real enigma lies in their shapes. Instead of perfect spheres, many bubbles appear distorted, with tendrils and cavities resembling foam in a sink. This suggests the interstellar medium isn't a uniform void but a complex, layered environment where hot bubbles interact with cold clouds in ways we're only starting to map. Some regions show bubbles punching through denser gas like blowtorches through ice, carving tunnels that could funnel heavy elements into interstellar space. Others seem to be stalled, their energy sapped by encounters with invisible magnetic barriers. Unraveling these mysteries isn't just academic, it's key to understanding how galaxies recycle matter and energy. These bubbles might be the universe's pressure valves, regulating star formation by heating surrounding gas and preventing premature collapse. or they could be galactic transporters, distributing the heavy elements forged in stellar cores across cosmic distances. Every flicker of X-ray light from their seething depths is a clue, waiting to reveal how the most violent forces in nature sculpt the quiet spaces between the stars. Until then, these million-degree anomalies remain one of space's most defiant puzzles, a reminder that even the emptiest corners of the cosmos are alive with invisible fire. Deuterium, the universe's heavy hydrogen, should be one of the most predictable elements in existence. Born mere minutes after the Big Bang, its abundance was locked in by the laws of physics during nucleosynthesis, a cosmic fingerprint that should remain nearly constant across space. Yet when astronomers measure its presence in the interstellar medium, the numbers refuse to behave. Some clouds show deuterium levels matching primordial predictions, while others reveal shocking deficits, as if this cosmic relic has been stealthily siphoned away over billions of years. The question is simple: how does an isotope forged at the dawn of time end up playing hide and seek across the galaxy, the prime suspect in this cosmic heist? Stars. When deuterium gets dragged into a star's core, it's obliterated, fused into helium almost immediately under the intense heat and pressure. This explains why older regions of the interstellar medium, recycled through multiple generations of stellar furnaces, show depleted deuterium. But the mystery deepens when we find younger, seemingly untouched gas clouds with similarly low levels. If stars aren't the only culprits, what other processes could be destroying or hiding this primordial isotope? Enter cosmic ray spallation, a dramatic process where high-energy particles smash into heavier atoms like oxygen or carbon, shattering them into lighter fragments including deuterium. It's like a celestial pool break where interstellar billiard balls crack apart to release fresh heavy hydrogen. This should theoretically replenish some of the lost deuterium, yet observations reveal wild inconsistencies. Some clouds along cosmic ray highways show expected spikes in deuterium, while neighboring regions bathed in similar radiation show baffling shortages. The discrepancy suggests hidden factors at play, perhaps magnetic fields funneling cosmic rays unevenly, or unknown chemical reactions locking deuterium into icy dust grains where telescopes can't detect it. Then there's the measurement problem. Deuterium's telltale signature lies in ultraviolet light, specifically a faint absorption line that's easily drowned out by interstellar dust. To map its distribution, astronomers rely on painstaking observations of background stars, each one a single pixel in a sprawling cosmic puzzle. Even then, the data comes with asterisks, variations in cloud density, temperature, and even local radiation fields can skew results, turning deuterium tracking into an exercise in astrophysical forensics. The stakes are higher than they seem. Deuterium isn't just another element, it's a benchmark for the universe's earliest moments. If its current distribution doesn't align with Big Bang predictions, it could hint at gaps in our understanding of galactic evolution, or even undiscovered physics governing how matter cycles through space. Every anomalous measurement is a breadcrumb leading us closer to answers, or deeper into the interstellar medium's tangled web of secrets. For now, the case of the missing heavy hydrogen remains wide open, a reminder that even the simplest atoms can hold cosmic mysteries. Somewhere in the Milky Way, a star explodes with the brilliance of 1 billion suns, a supernova so powerful its light outshines entire galaxies. We know these cataclysms happen roughly once every 50 years in our corner of the cosmos. Yet when astronomers scan the skies for their remains, something doesn't add up. Half the ghostly husks left behind, the expanding bubbles of gas and dust we call supernova remnants, are missing. It's like investigating a crime scene where the victims vanish without leaving bodies. So where did they go? The answer might rewrite how we understand the life cycle of stars and the hidden architecture of our galaxy. The first clue lies in the remnants we can see. Take the Crab Nebula, a dazzling web of filaments glowing from a star that died in 1054. or Cassiopeia A, whose shockwaves still ripple outward at 15 million kilometers per hour 1,000 years after the explosion. These structures follow a familiar script, a rapidly expanding shell of debris, energized by the dying star's final scream. But mathematical models suggest we should be seeing twice as many of these cosmic gravestones scattered across the Milky Way. The discrepancy grows starker when radio telescopes peer into the galaxy's crowded core, where stellar density should make supernova even more frequent. Instead of a cemetery of remnants, they find eerie voids, silent patches where the dead should be. One explanation is as unsettling as it is elegant. Some supernova remnants don't fade, they dissolve. Imagine pouring ink into a turbulent river. At first, the stain holds its shape, but soon the currents tear it apart until no trace remains. Similarly, in regions where the interstellar medium is especially chaotic, supernova debris might disperse so thoroughly it becomes indistinguishable from the surrounding gas. Computer simulations reveal this process could accelerate in environments laced with powerful magnetic fields, which might shred remnants into diffuse, invisible tendrils within mere millennia, a blink in cosmic time. But there's a darker possibility. Some missing remnants might not have vanished at all. They could be hiding in plain sight, camouflaged as ordinary gas clouds. When a supernova explodes near a dense molecular cloud, its ejecta don't form the classic bubble. Instead, they burrow into the cloud like a bullet fired into snow, leaving no clean crater behind. Infrared observations have spotted a handful of these stealth supernova, their presence betrayed only by unusual chemical enrichments or telltale heat signatures. The rest could be lurking undetected, their energy absorbed by the very clouds that conceal them. The plot thickens when we consider the galaxy's kiloparsec voids, vast regions where young stars and supernova remnants are conspicuously absent. These cosmic deserts shouldn't exist if supernova distribute their debris evenly. One radical theory suggests ancient supernova in these zones might have blown their remnants clean out of the galactic disk, launching them into the halo like interstellar fireworks. Supporting this idea are the so-called high-velocity clouds streaking above the Milky Way, some of which carry chemical signatures matching supernova ejecta. If true, it means our galaxy's missing stellar corpses might not be missing at all, just exiled. Every undetected remnant is a lost chapter in the galaxy's history. Without them, we can't fully account for the heavy elements they scatter, the very stuff of planets and life. Their disappearance warps our calculations of how often stars explode, how energy cycles through the interstellar medium, even how galaxies evolve. The hunt for these silent supernova legacies isn't just about solving a cosmic accounting error, it's about piecing together how violence and chaos sculpt the universe's grandest structures, one invisible ghost at a time. Stretching across unimaginable distances, the universe is threaded with glowing filaments of gas, like a cosmic spiderweb spun on the scale of galaxies. These are the tendrils of the intergalactic medium, vast rivers of hydrogen and helium winding through the darkness, connecting galaxy clusters in a shimmering network. Picture them as celestial highways, funneling gas across millions of light years to feed starving galaxies, yet so tenuous that if you stood inside one, you'd swear you were in a perfect vacuum. Observing these filaments directly is like trying to spot a single strand of silk in a moonlit forest. Their density is so low, just a few atoms per cubic meter, that they barely leave a trace on telescopes. But here's the trick astronomers use. When light from distant quasars pierces these structures, certain wavelengths get absorbed, revealing the filament's hidden presence like shadows cast on a cosmic curtain. The most stunning confirmation came from the Hubble Space Telescope, which mapped a filament stretching 60 million light-years between two galaxy clusters, glowing faintly with the ultraviolet signature of ionized hydrogen. What keeps these fragile structures from collapsing? The answer lies in the universe's most mysterious architect, dark matter. Though invisible, its gravitational scaffolding holds the cosmic web taut, guiding gas into rivers that flow along predetermined channels. Simulations show these filaments aren't static, they pulse and ripple as galaxies move, sending shockwaves through the intergalactic medium like vibrations along a plucked string. Some regions resemble braided deltas, where multiple strands twist together before feeding into galaxy clusters like water swirling down a drain. Yet for all their elegance, these filaments harbor puzzles. Why do some appear choked with heavy elements, carbon, oxygen, even neon, while others remain pristine, untouched by stellar furnaces since the Big Bang? The answer might rewrite how we think galaxies share resources. Supernova and active black holes could be blasting enriched material far beyond their galactic borders, seeding the cosmic web with the raw ingredients for future stars. Other filaments show bizarre temperature swings, with pockets of gas blazing at millions of degrees alongside regions colder than the void between stars. Magnetic fields might explain the contrast, acting as cosmic insulators that trap heat in some zones while letting it bleed away in others. Zoom out far enough, and the web reveals its grandest secret. It's the universe's circulatory system. Without these filaments, galaxies would starve, isolated in islands of darkness. Every second, our own Milky Way gulps down fresh gas from the local sheet, a filamentary structure wrapping our galactic neighborhood. Yet for all we've uncovered, most of this network remains uncharted, a hidden geography written in whispers of gas and shadows of light waiting to be decoded. Buried in the mud of Earth's deepest oceans, a radioactive whisper from the cosmos lingers, iron-60, an isotope so rare it shouldn't exist here naturally. This isn't just another element, it's a celestial breadcrumb, a smoking gun pointing to violent stellar explosions that rocked our galactic neighborhood within the last few million years. Think of it as cosmic forensics. The interstellar medium doesn't just host mysteries. It occasionally drops evidence right on our planet, and this particular clue suggests we've been bathing in the fallout of ancient supernova without even realizing it. Iron-60 is forged in the final moments of massive stars, when collapsing cores reach temperatures so extreme that atoms are ripped apart and reassembled under unimaginable pressure. Under normal circumstances, it decays into nickel-60 within 2.5 million years, a geological blink. So when scientists drilled into oceanic crust and found traces of this short-lived isotope, the implication was staggering. Fresh supernova debris had rained down on Earth long after the dinosaurs vanished, but recent enough that its radioactive signature hasn't completely faded. The discovery sent researchers scrambling to map its distribution, revealing layers of iron-60 sprinkled across the Pacific, Atlantic, and even Antarctic ice cores like cosmic confetti. But how did it get here? The journey begins in the chaos of a dying star's explosion, where iron-60 gets blasted into space at nearly 1/10 the speed of light. For centuries, these atoms drift through the interstellar medium, buffeted by magnetic fields and mingling with other stellar debris. Unlike heavier elements that clump into dust grains, iron-60 stays solo, a lone wolf riding the galactic winds. Eventually, our solar system plows through one of these radioactive clouds, sweeping the isotope into the sun's gravitational embrace. Some gets trapped in asteroids or comets, but a fraction slips past, drifting down through Earth's atmosphere and settling silently into sediments. The real shock came when researchers pinned down the timing. The iron-60 spikes in our ocean floors align with two distinct periods around 2.5 million years ago, and again just over 1 million years back, suggesting not one, but multiple supernova erupted frighteningly close to Earth. Close in cosmic terms, of course, these stars likely detonated within a few hundred light years, far enough to avoid sterilizing the planet, but near enough to drench it in radioactive fallout. Sediment layers from those eras also show elevated rates of extinction and climate shifts, raising eerie questions. Did these stellar cataclysms alter Earth's biology? Could supernova have pruned the evolutionary tree, clearing the way for new species, including our own ancestors? even stranger is the iron 60's uneven spread. Some ocean basins show concentrated deposits, while others are nearly clean, hinting that the isotope didn't arrive in a steady drizzle but in concentrated waves, perhaps carried by dense interstellar clouds our solar system passed through. Astronomers have even identified possible suspects: the Scorpius-Centaurus Stellar Association, a nearby nest of massive stars that since drifted apart, some of which could have exploded right on our cosmic doorstep. What makes this mystery so gripping is its intimacy. We're not just observers of the interstellar medium, we're participants collecting stardust in our planet's geological archives. Every atom of iron 60 is a timestamp, a relic of stellar violence that touched Earth itself. And the story isn't over. Scientists now scour the oceans for fresher traces, wondering if we're still passing through the remnants of those ancient explosions. The universe doesn't just whisper its secrets across light years. Sometimes it tucks them into the mud beneath our feet, waiting for us to dig them up. The interstellar medium should be the calmest place imaginable, a near-perfect vacuum where gas atoms drift lazily, only bumping into one another every few years. Yet astronomers see something radically different, a churning, storm-tossed sea where gas swirls in turbulent eddies so violent they dwarf Earth's worst hurricanes. This is the turbulence paradox, a baffling contradiction where space's emptiness somehow behaves like a roiling ocean. The sheer violence of these motions defies intuition. How can a handful of atoms per cubic centimeter whip itself into such frenzy without wind, without water, without anything resembling a medium to carry the chaos? The leading suspect, supernova, those stellar detonations packing enough punch to disturb gas across hundreds of light years. Picture a bomb exploding underwater, sending shockwaves that roil the surface long after the initial blast. When a massive star dies, it doesn't just vanish, it slams into the surrounding interstellar medium like a cosmic sledgehammer, creating expanding bubbles of hot gas that ripple outward at thousands of kilometers per second. These shockwaves don't just push material, they twist it, fracture it, and leave behind a wake of instability. Observations back this up. Regions littered with supernova remnants often show gas moving in bizarre, tangled patterns like smoke caught in a whirlwind. Yet for all their destructive power, supernova might not be the sole architects of this turbulence. Some gas clouds exhibit violent motions far from any recent explosions, suggesting a hidden hand at work. That's where galactic rotation enters the picture. The Milky Way isn't a static disk, it's a spinning carousel with spiral arms and gas clouds moving at different speeds. This differential rotation stretches and shears interstellar material, injecting energy like a giant mixer churning cosmic batter. Magnetic fields add another layer, acting as invisible wires that tangle and snap, transferring energy across vast distances. The result, gas that should be drifting placidly instead behaves like cream stirred into coffee, full of unpredictable swirls and eddies. But the mystery deepens when we compare theory to observation. Computer simulations struggle to replicate the interstellar medium's turbulence without overloading it with energy. If supernova and rotation were the only sources, gas motions should die down much faster than they do, like a ripple fading in a pond. Instead, turbulence persists even in isolated regions where no obvious energy source exists. Some researchers speculate that interstellar gas might be self-sustaining. Once stirred up, it generates its own chaotic motions through cascading interactions, like dominoes that keep falling in an endless loop. Others propose more exotic explanations, from the gravitational whispers of dark matter to unresolved micro-explosions of unknown origin. The stakes are higher than they seem. Turbulence doesn't just ruffle gas clouds, it shapes the fate of galaxies. Without it, star-forming regions would collapse too quickly, birthing only massive stars. With it, the interstellar medium becomes a cosmic pressure valve, regulating how and where stars ignite. every swirling eddy, every shockwave-rippled cloud is a piece of a puzzle we've only just begun to assemble, one where emptiness somehow holds the fury of a storm. Carbon should be everywhere in the interstellar medium after all. It's the fourth most abundant element in the universe, forged in the hearts of stars and scattered across galaxies by supernovae. Yet when astronomers tally up all the carbon they can detect floating between the stars, nearly half of it is missing. The numbers don't add up. Imagine pouring a bucket of water into a pond, only to watch half vanish without a trace. That's the scale of this cosmic accounting error, and it's forcing scientists to rethink where, and in what form, the universe's fundamental building blocks might be hiding. One leading theory points to dark molecular clouds, those shadowy regions of space so dense they swallow starlight whole. These cosmic vaults could be hoarding vast reserves of carbon in forms our telescopes struggle to see. Picture a bank heist where the thieves don't take cash, they convert it into untraceable assets. Similarly, carbon in these clouds might have frozen onto dust grains or bonded into complex, dark molecules that don't emit the telltale spectroscopic signatures astronomers rely on. Laboratory experiments back this up, showing carbon can form refractory compounds, tough, heat-resistant structures that cling to interstellar grit like cosmic barnacles, effectively disappearing from view. But dark clouds aren't the only suspects. Some researchers speculate a fraction of the missing carbon could be locked away in rogue planets, worlds untethered to any star, drifting through interstellar space like ghostly nomads. These solitary orbs, ejected from their birth systems by gravitational chaos, might carry frozen oceans of carbon-rich ices or even layers of diamond-like carbon deep beneath their surfaces. It's a haunting thought, billions of invisible worlds, each a potential carbon reservoir, slipping through the darkness undetected. The math is tantalizing. If just one in every few thousand stars spawns a rogue planet, their combined mass could account for a significant chunk of the deficit. Then there's the wild card, cosmic graphite. Unlike the sooty PAHs we've detected, larger sheets of graphene-like carbon could lurk in the interstellar medium, structured like microscopic chicken wire. These sheets wouldn't emit much light, but they'd absorb it efficiently, effectively cloaking themselves in plain sight. The James Webb Space Telescope has spotted hints of such structures in the infrared glow of certain nebulae, but the data remains frustratingly vague. Are we seeing the tip of a carbon iceberg or just another dead end? The implications stretch far beyond bookkeeping. Carbon isn't just another element, it's the backbone of life, the scribe of cosmic chemistry. If it's hiding in forms we can't yet detect, our entire understanding of how planets and organic molecules form could be skewed. Every missing carbon atom is a clue, a whisper from the dark corners of the interstellar medium, waiting to reveal where the universe stashes its most precious ingredients. Until we solve this puzzle, our maps of the cosmos remain incomplete, like trying to read a book with half the pages torn out. In the beginning, when the universe was a searing soup of particles too hot for atoms to form, one molecule defied the chaos: helium hydride. A fragile union of a helium atom and a hydrogen ion, this delicate pairing holds the title of the universe's first chemical bond, forged when the cosmos was just 100,000 years old. For decades, it existed only in theory and lab experiments, a ghost from the primordial past. Then, in 2019, astronomers finally spotted its faint infrared signal in a distant planetary nebula, a discovery that made headlines worldwide. But here's the twist: finding it was like stumbling upon a single fossilized footprint in an empty desert, a proof it once existed, yet vanishingly rare in today's universe. So where did all the helium hydride go? The answer lies in the interstellar medium's changing chemistry. Back in the universe's infancy, conditions were perfect for helium hydride to thrive. A dense, scorching plasma where helium and hydrogen ions collided constantly. But as space expanded and cooled, neutral atoms began to dominate, and this delicate molecule faced a brutal ultimatum: give up its helium or be destroyed. Hydrogen, now no longer ionized, became a jealous partner, yanking helium away to form molecular hydrogen, the workhorse of modern interstellar chemistry. The very environment that birthed helium hydride became its executioner, erasing nearly every trace of it within a few million years. Yet its scarcity isn't just a relic of the past. Even today, in the harsh corners of the interstellar medium where conditions mimic the early universe, supernova shocks, violent stellar winds, or the energetic cores of planetary nebulae, helium hydride flickers briefly into existence only to vanish again. It's like a cosmic mayfly, living for just a fleeting moment before the relentless chemistry of space tears it apart. The fact that we've detected it at all is a testament to how meticulously the universe preserves its oldest recipes, even when the ingredients have long since changed. What makes this molecule so scientifically precious isn't just its rarity, it's a benchmark, a touchstone for testing our models of cosmic evolution. When simulations of the early universe fail to reproduce the expected helium hydride signatures, it's a clue that we're missing something fundamental about how matter behaved during those first critical epochs. Some theories even suggest that pockets of primordial gas, untouched by star formation, might still harbor traces of it, hiding in plain sight like linguistic holdovers in an ancient dialect. Then there's the irony. Helium hydride's fragility makes it a powerful tool. In modern nebulae, its presence or absence reveals the violence of stellar environments. Where it lingers, we're essentially watching the interstellar medium reset to its primal state, a brief reenactment of chemistry's first act. Each detection is a time machine, offering a glimpse into the moment when the universe transitioned from a featureless plasma to a stage rich with molecular diversity. The hunt for more helium hydride isn't just nostalgia for the cosmos's earliest moments. It's a reminder that the interstellar medium isn't a static backdrop. It's a dynamic, evolving system where molecules rise and fall like civilizations. And somewhere in the turbulence of space, between the birth and death of stars, this elusive compound still whispers its story, waiting for us to listen. Deep in the icy voids between stars, where temperatures plunge hundreds of degrees below freezing, molecules that shouldn't exist are thriving, like ethylene glycol, the same antifreeze you might pour into your car's radiator. This cosmic cocktail ingredient, along with other complex organic compounds, lurks in frigid interstellar clouds, defying the harsh reality of space. How does chemistry this intricate occur in an environment more barren than any lab-created vacuum, where atoms might collide once every century? The answer lies in a hidden alchemy, one where time, dust, and cosmic radiation conspire to build complexity where simplicity should reign. Picture a grain of interstellar dust, no larger than a virus, coated in a shell of ice. This microscopic speck becomes a floating chemistry lab. When ultraviolet light or cosmic rays strike it, they break apart simple molecules like water or methane frozen on its surface, creating reactive fragments. These fragments, atoms with unpaired electrons desperate to bond, skitter across the grain's surface until they find partners. Over millennia, this slow-motion dance builds molecules of startling complexity. Ethylene glycol doesn't form in one dramatic reaction, but through countless tiny steps, like a puzzle assembling itself one piece per year. Lab experiments on Earth mimic these conditions by freezing gases to near absolute zero and zapping them with radiation, and sure enough, familiar antifreeze emerges. The kicker: space does it better. Without gravity or convection to interfere, reactions play out with eerie precision, yielding compounds lab setups often miss. Yet ethylene glycol is just the tip of the iceberg. Telescopes have spotted even wilder molecules floating between stars, from vinegar-like acetic acid to sugar-related glycolaldehyde. Some clouds contain enough of these compounds to fill trillions of comets, raising tantalizing questions. Could these interstellar factories have seeded young planets with life's building blocks? The chemistry works both ways, though. Just as these molecules form, the same radiation that creates them can tear them apart. It's a cosmic balancing act with destruction and creation locked in a delicate dance. The real mystery isn't just how these molecules form, but why some clouds become organic hotspots while others remain barren. Magnetic fields might funnel energy in ways that favor certain reactions, or perhaps turbulence concentrates key ingredients like a chef reducing a sauce. Every detection of a new interstellar molecule forces us to rethink the limits of chemistry in the universe's most unforgiving environments. And lurking in that rethinking is a humbling possibility that the recipe for life's ingredients isn't special to planets at all, but written into the very fabric of the cosmos, waiting in the dark between the stars. The interstellar medium should be dark, not just the absence of starlight, but a void where high-energy gamma rays are rare and fleeting. Yet when astronomers point their telescopes at seemingly empty patches of sky, they find an eerie, uniform glow of gamma radiation, as if the entire galaxy is bathed in an invisible fog. This isn't the work of black holes or supernovae. Those create pinpoint bursts of energy. This glow is different, diffuse, persistent, and maddeningly unexplained. Some call it the gamma-ray haze, and it's forcing scientists to reconsider what might be lurking unseen in the spaces between stars. One possible culprit. Pulsars, those rapidly spinning neutron stars that act like cosmic lighthouses, beaming radiation across the galaxy. When their high-energy particles collide with interstellar gas, gamma rays can spark into existence like sparks from a grindstone. The Milky Way's central regions, thick with ancient pulsars, show the strongest gamma-ray fog, lending weight to this theory. But here's the catch. Even if you tally up every known pulsar, their combined output can't account for the sheer volume of gamma rays we detect. There's too much glow, too evenly spread, as if something else, something far subtler, is at work. That's where dark matter enters the scene. Some theories suggest this elusive substance, which makes up 85% of the universe's mass, might occasionally annihilate itself, releasing gamma rays in the process. Picture two invisible particles colliding in deep space, dissolving into pure energy. If true, the gamma-ray fog could be the first indirect glimpse of dark matter's hidden fireworks. Yet the distribution doesn't quite match predictions. The glow extends farther from the galactic center than most dark matter models allow, leaving researchers to wonder if they're missing a critical piece of the puzzle. Then there's the wild card, cosmic rays slamming into hidden reservoirs of gas. We know the interstellar medium is riddled with cold, dark clouds too diffuse to see directly. When high-energy protons from cosmic rays plow into these clouds, they can trigger gamma-ray emission like a match struck in a dusty cellar. The trouble is, these interactions should produce a very specific energy signature, and the gamma-ray fog doesn't quite fit. It's too smooth, too uniform, as if an unseen hand is stirring the pot. The implications ripple outward. If pulsars are the primary source, we might need to reevaluate how efficiently these dead stars pump energy into space. If dark matter is involved, it could reveal clues about its true nature, not just where it hides, but how it behaves. And if hidden gas clouds are the key, we're staring at an entire shadow universe of matter we've barely begun to map. What makes this mystery so gripping isn't just the unanswered question. It's the possibility that whatever explains the gamma-ray fog might rewrite our understanding of the interstellar medium itself, revealing a cosmos far more dynamic and mysterious than we ever imagined. Among the drifting particles of interstellar dust, an eerie cosmic choreography unfolds, one that shouldn't be possible. These microscopic grains, no larger than smoke particles, spin and sway in perfect alignment with the galaxy's invisible magnetic fields, bending starlight like a celestial fingerprint. It's a phenomenon called starlight polarization, and it's one of the interstellar medium's most elegant puzzles. Imagine billions of tiny compass needles, each one a speck of dust, all pointing the same direction across light years of space without a single collision to guide them. How does chaos give way to such precise order? The secret lies in the dust shape. Unlike the symmetrical spheres we might picture, interstellar grains are jagged, lopsided things, more like broken shards of pottery than perfect marbles. When starlight strikes them, its electric field tugs at their uneven surfaces, nudging them to align perpendicular to the light's path, but magnetism adds another layer. Many of these grains contain metallic flex iron or nickel atoms embedded in their structures, turning them into makeshift magnets. Galactic magnetic fields, faint as they are, seize on this property, coaxing the grains into a slow, synchronized pirouette. The result, a vast floating filter that polarizes starlight, imprinting it with invisible signatures of the fields it traversed. This dance isn't just a cosmic curiosity, it's a cornerstone of star birth. As these aligned grains drift through molecular clouds, their movements shape the very fabric of future solar systems. When gravity begins pulling a cloud's gas inward, the dust's magnetic properties resist the collapse, channeling material into flattened disks rather than chaotic clumps. Picture a potter's wheel spinning clay into symmetry. Without this magnetic guidance, protoplanetary disks might never form, leaving planets to emerge from chaos rather than orderly orbits. Yet even this well-rehearsed ballet has its mysteries. Some regions show dust aligned in ways that defy magnetic field maps, as if hidden currents are tugging at the grains. Others exhibit polarization patterns that twist and warp unnaturally, hinting at turbulence or even undiscovered magnetic structures lurking within the clouds. The James Webb Space Telescope recently captured infrared glimpses of these anomalies, dust spirals in the Orion Nebula coiled like cosmic snakes, their alignment mismatched with surrounding fields. Are we seeing the handiwork of stellar winds sculpting the dust like invisible fingers, or something stranger like the imprint of dark matter's gravitational whispers? What makes these grains so captivating is their duality, both canvas and artist. They reveal the hidden architecture of magnetic fields while actively shaping the birthplaces of stars. Every flicker of polarized starlight is a message, a ripple in the interstellar medium's grand design. And as we decode their movements, we're not just solving a puzzle, we're learning the steps to the universe's oldest dance, one that's been choreographing solar systems since the dawn of galaxies. We live inside a cosmic bubble, not a metaphor, but a literal cavity in the interstellar medium, a thousand light-year-wide void where the Milky Way's usual gas and dust thin to near nothingness. This is the local bubble, our solar system's home turf, and it's anything but ordinary. Picture the galaxy as a bustling city, with dense molecular clouds like towering skyscrapers and star clusters as crowded neighborhoods. The local bubble, it's the empty lot at the center of it all, a silent sphere of sparse, superheated gas where the usual interstellar clutter has been swept clean. But by what? The answer could rewrite the history of our galactic backyard. The most dramatic explanation points to a series of supernovae, not one or two, but a chain reaction of stellar explosions that detonated like cosmic grenades roughly 14 million years ago. When massive stars die, they don't go quietly. Their shockwaves rip through surrounding gas, carving out cavities and pushing material outward like a snowplow clearing a highway. Trace the motions of nearby star clusters like the Scorpius-Centaurus Association, and you'll find their oldest members are perfectly positioned to have unleashed these cataclysms, their blast waves overlapping to sculpt the bubble we see today. X-ray observations back this up, revealing the bubble's interior glowing faintly with million-degree plasma, the lingering heat of those ancient blasts. Yet there's a rival theory that trades stellar violence for sustained, patient force. Imagine a group of young, massive stars, their fierce stellar winds streaming outward for millions of years like unrelenting gales. Over time, these winds could have hollowed out the local bubble as effectively as supernovae, like a river gradually carving a canyon. The O-type stars in Orion's ancestral family are prime suspects. Their short, brilliant lives would have bathed nearby space in relentless radiation pressure, gradually evacuating the gas. Supporters of this idea point to the bubble's uneven walls, which lack the crisp symmetry expected from explosive origins, suggesting a slower, messier sculpting process. What makes this debate so pivotal isn't just academic curiosity, it's a window into how galaxies regulate their ecosystems. If supernovae dominate, it means these explosions are the universe's ultimate landscapers, redistributing matter and energy in violent, punctuated bursts. But if stellar winds take the lead, it implies a quieter, more continuous reshaping of space, where even the gentlest stellar breezes can leave lasting marks. The local bubble's very shape holds clues. Its interior is laced with delicate filaments of warm gas, structures too fragile to have survived supernova shocks but perfectly consistent with wind-sculpted models. Even stranger is the bubble's ongoing evolution. Our solar system isn't just floating passively inside it, we're moving through its walls at 70,000 kilometers per hour. Within the next few million years, we'll exit the bubble entirely, plunging into denser interstellar territory. What happens then? The last time our ancestors ventured beyond such a protective cavity, Earth may have been bombarded with higher levels of cosmic radiation, leaving isotopic traces in deep-sea sediments. The local bubble isn't just a relic, it's an active player in our planet's cosmic environment, its boundaries shifting like tides against the shores of our solar system. The deeper we probe, the more the bubble defies simple explanation. Some regions along its edges show bizarre chemical enrichments, heavy elements like iron and silicon, concentrated in ways that hint at multiple overlapping processes. Other sections appear almost pristine, as if untouched by stellar influence entirely. Mapping these variations is like deciphering a palimpsest where layers of galactic history have been written, erased, and rewritten over eons. Every new observation peels back another layer, revealing not just how our corner of space came to be, but how all such bubbles might shape the births and deaths of stars across the cosmos. For now, the local bubble remains both familiar and profoundly mysterious, a home we're still learning to understand. Its emptiness is an illusion, its quiet a mask for the violent or patient forces that shaped it. Whether forged by supernova or stellar winds, its existence reminds us that even the void has a story, one that's still unfolding around us, light year by light year. From ghostly dark gas clouds to rogue molecules that defy chemistry, from missing matter to interstellar soot older than our solar system, the interstellar medium isn't just the backdrop of the cosmos, it's the universe's greatest unsolved puzzle box. Every mystery we've explored isn't isolated, they twist together like strands of a cosmic braid. The same turbulence that shapes star-forming clouds also scatters deuterium. The magnetic fields propping up cold molecular clumps are the same invisible threads aligning interstellar dust. Even the humblest speck of space soot is linked to the explosions of massive stars, their death seeding the galaxy with the very ingredients for new worlds. Consider how the local bubble, our own celestial neighborhood, carries echoes of supernova that exploded millions of years ago, while the gamma-ray fog hints at processes still unfolding in the darkness. Iron-60 buried in Earth's oceans and helium hydride flickering in distant nebulae are reminders that the interstellar medium isn't some distant abstraction. It's a dynamic, evolving ecosystem, one we're swimming through right now, bathed in starlight filtered by dust grains older than our planet. What makes these mysteries so thrilling isn't just their complexity, it's how little we've scratched the surface. For every answer, 10 new questions erupt. Why do some molecular clouds collapse into stars while others linger frozen? How does gas threaded with magnetic fields resist gravity's pull? What hides the universe's missing carbon or lithium, or half the supernova remnants we know must exist? Each enigma is a doorway inviting us to rethink not just the spaces between stars, but the fundamental laws governing everything from chemistry to cosmology. The interstellar medium is more than empty space. It's the universe's workshop, its archive, its canvas. Every discovery peels back another layer, revealing connections between the smallest molecules and the largest cosmic structures. And with telescopes like James Webb and upcoming missions like the Square Kilometre Array, we're on the verge of breakthroughs that could rewrite textbooks. So the next time you gaze at the night sky, remember, the darkness between the stars isn't empty. It's a frontier brimming with questions, waiting for curious minds to piece them together. The greatest cosmic story isn't just written in the stars, it's hidden in the whispers of the interstellar medium, and we're only just learning to listen.